And studied nuclear chemistry, and we looked at radioisotopes. Yeah, here in a minute. Not yet. So, radioisotopes, there are different types of isotopes, right? You have stable isotopes and you have radioisotopes. So, how old do you feel? Raise your hand, tell me, how old do you feel?
90, my bones hurt.
Raise your hand. How old do you feel?
I feel like 12.
You feel like 12?
Yeah.
Okay.
40. 40-ish.
40-ish. Claire, how old do you feel?
I can't eat bad foods anymore. That's why I'm
like
getting
a
older.
4-year-old.
My body
Like
got
4-year-old?
the
Yeah.
difference.
Now, I'm asking this question associated, Cody, I'm asking this question associated with your body. You know, how old does your body feel?
We're about to get into carbon dating again.
Yeah, we're going to just review it because we talked about it last semester. But this concept, remember, you're made of these elements, right?
Yeah.
So the question is, well, which ones are radioisotopes, which ones are stable, and how much of your body is made of stable isotopes compared to radioisotopes?
It's like a bus. It's like one.
Now remember,
Spontaneous combustion.
the stable isotopes do not have what? Stable isotopes do not have what? Stable isotopes do not have a predictable death. So write that down. Stable isotopes do not have a predictable.
So they live forever.
Right.
So kind of like carbon, whatever it is.
Now that doesn't mean they can't die, right? You can walk out in front of a bus and get hit, but that's not something we can predict. Does everybody understand? Accidents happen, but we can't use accidents to predict what's going to happen to you. And that's what you can see with carbon. Carbon is so stable, enough accidents do not happen to give us a predictable death. Now, if if enough people were getting struck by cars, or were in accidents, the insurance company can give you a prediction of when you will have an accident, because enough people have accidents. So if we notice enough carbon-12 changing into carbon, or changing into another element, then we would be able to predict its death. You understand?
Have you ever met those people that only turn a certain way because it's less likely to get hit?
Just right here are what the class predicted would be radioisotopes for oxygen. So let's take a look at oxygen.
We kind of can't.
So right here you'll see that oxygen 16, oxygen 15, oxygen 16, oxygen 17, oxygen 18 are all stable. Now if you notice there, no, it's like 0% is radioactive. Now what does that mean? It means that 65% of your body right now has no predictable death. 11 is synthetic, so it's going to not really exist inside of you. It's got a 20-minute decay cycle. The ones you're going to see the most of are carbon-12 and carbon-13. What's 98.9 plus 1? 99.9, and then there's a 0.1, so 100% of it is pretty stable. Now you're probably thinking, well, Mrs. Steinecker, then how can they determine when you die how old you are? This trace right here, this trace amount is such a small amount, we can't even put it on a balance to measure. It has to be radioactively detected with a detector. That's why they say trace amounts. It's a very small amount. It can be detected, yes, but it cannot be put on a balance and measured. So pretty much 100% of your carbon, that would be 18 plus oxygen. You'll notice that if you looked at all the other elements that are in you, that is about 99% of them are stable. So you're walking around and you are experiencing, Claire, your body is made of elements, atoms that have been around for a very, very long time, that are stable.
So when I die, I'm just going to choke.
Yeah, well, I mean, things want to react with you. It's called chemical reactions. There are chemical reactions that will take place when you die,
Like
decay processes and things like that. But if we could keep you, and like put you in a vial and send you to outer space, keep you there, isolated, yeah, your body would stay in that state for a very long time. Now, space is full of a lot of violent reactions, and just the background radiation and things like that. That's going to cause you to want to break apart. So keep that in mind. That you're together as a whole. All those elements are working together to make you, but all of them independently are very stable. So you're experiencing very old. I guess you'd say characteristics.
Does that mean like some part of me is like 1,000 years old?
No. There's very trace of you that's that way. You are, billions of years old. You are so old. You are so old that we can't even date you.
Dang, you just got roasted.
Yeah. You're so old we can't even date you. That is, if we were to try to figure out how old the Earth was by looking at you, it couldn't be done. Nice job, man.
What was the highest point on that?
Nice job, Dale Sean. Driving an automobile. Now, when you drive and you have an accident, insurance companies can predict when your next accident will be. For most people, they have an accident every 15 years. So accidents are common enough where we can then predict when your next one will be. Is everybody clear? Right? So carbon-14, its death is predicted to be around 5,000 years. So the question is, how much of the carbon within you has a predictable death? And that's what you would feel. You'd be like, well, that's new, so I should feel that newness because it's only about 5,000 years old. Make sense? So if the carbon in you is the majority of the carbon, let's say if 95% of the atoms within you were formed within the last 5,000 years, then you should feel around 5,000 years old, right? Make sense? Everybody understand? That 100% of oxygen is stable. Now, there's a trace that's not, but we're not going to get into that. But the point is that if you died today, we could not use you to determine the age of the Earth because you're so stable. 98.9 plus 1.1 is 100. That would be 100% carbon is stable. When they say trace, it's such a small amount we can't measure it on a balance. That is, this balance right here would be useless to determine the amount of carbon-14 inside of you. So if we isolated all the carbon within you, it's a black substance, pure carbon is. Kind of looks like charcoal. We could do that with you. Just put you in the oven and bake you and then separate you, the carbon powder there. Yeah. Carbon-12 and carbon-13 are just that stable. They do not have a predictable death. The trace amount would have to be determined by a radioactive counter. We could not put it on a balance and measure it.
Exotic organisms teeming around a coral reef, such as the one shown in Figure 7.1. The coral was formed from
Gases have electron configurations that have a full outermost energy level. This level is filled with two
and metallic bonding. Well, metallic bonding is kind of like alloys, metals. They don't tend to form crystals. Now, this up here on the ceiling, these are called crystals. And this one right here is the water crystal. Now, if you notice right there, that crystal is not a perfect square. It's called hexagonal, compared to the sodium chloride over there, which is cubic. The cubic is an actual square, and the crystal structure is the reason why salt is separate from water when it freezes. Water forms a crystal when it freezes, and so does the salt. Salt is pushed out of the water, and you can go to the North and South Pole and see the icebergs to prove that. And the covalent compounds form crystals. The metallic do not. And this is the reason why metallic bonds are very difficult to predict when you're making, let's say, a metal for a bicycle or a car. To be consistent is the goal. And you want to have those metals in the right place to form the best bond. but they're not repetitive. So that makes it very difficult to predict the behavior consistently of metallic bonds. Now, nanotechnology is, the goal of nanotechnology is to be able to consistently make the same type of metal where you have the atoms placed exactly where you want them. But that's not easy to do with the metallic bonding. Those are alloys, not compounds. Compounds form repetitive bonds, whereas mixtures do not. And metallic bonding is associated with mixture.
Do I do the top one?
Nitrogen is right here. You're just gonna copper that. You need a pencil. Nice job. Let me give about another stable that it does not have a predictable death. Now, when we say trace, what does that mean? It means you cannot put it on a balance and measure it. That is, if you died and we were to find the carbon-14, which you do have carbon-14 in you, but we couldn't put it on a balance and measure it. It's just too small of an amount. It can be detected radioactively, but it's just too small of an amount to actually detect it and measure it using a balance. So matter can change. That is, carbon can change into nitrogen and nitrogen can change into carbon. There's a cycle for that. And they're very different. Nitrogen is a gas, carbon is a solid. It just doesn't happen as frequently as it would make a difference for you. Like you see up here, 100% would be stable. So your body is timeless in a sense that we cannot predict when it will die or change into something else, the atoms. So keep that in mind when you get older and you're in a nursing home and you feel really old. Just keep in mind that, well, the atoms that make me up really are, stable. Just remember that word, stable. Do not form crystals. Why do metallic bonds not form crystals? Because they're not compounds. They are mixtures. And mixtures are just not repetitive. And because they're not repetitive, you don't get the ability to form a crystal. Crystals have to be repetitive. Now this one is not how they want your carbon drawn. They want it to follow this pattern right here.
It is on that pattern.
Actually, it's in the fourth group right there. So it should have a dot around it like that. Abundant metal in your body. No.
Oh, magnesium, cuz.
No.
Bromide.
Copper.
Cameron, no.
Silver.
No.
Gold.
Most abundant element in your body.
Wait. Zinc.
No.
Bronze.
No.
Wait.
Calcium, very good. Good job, Zadie.
By the 4 dots around the symbol C in the table.
Also recall that ionization energy refers to how easily an atom loses an electron, and that electron affinity indicates how much attraction an atom has for an electron. Known gases, their high ionization energies and low electron affinities show a general lack of 2 electrons per helium.
1s2.
In a repetitive pattern. So not every piece of iron or every sword is going to be the same or dependable. Crystals make dependable things. When you have, why is metallic bonding not dependable? It's a mixture. Alex, how are you? So Emma, this right here, you're going to copy right there. That's on the board. Of 98.9%, or that is the abundance, and then carbon-13 is 1.1%. So what is 98.9 plus 1.1, Noah? Yeah, it's 100%. So Emma, 100% of carbon inside of you is stable. Now you're probably thinking, well, Mr. Steinecker, how can that be true? If I die 80,000 years ago, they can date me based on carbon. Yes, So how much of the carbon-14 is inside of you? Noah, a trace amount. What does trace mean, Noah? Yeah, trace means a small amount. Trace means, Emma, the amount is so small we can't put it on a balance to measure it. Does it make sense? Trace? You understand trace? That's what they're saying right here. It says trace. It won't fit on a balance. It's such a small amount. Now we can measure it with a radioactive counter to determine that it's there, but there's such a small amount of it, it's not even included in the percent. So if you add it all, really all of them are stable, and you look at it, these 96% of you is stable. Really more than that, it's almost 100%. There's a trace amount of you that's radioactive. So you're walking around as you're feeling these elements are older than the earth. It's pretty wild when you think about it. Because often you don't really think about that. You see so much death, and you see so much change around you, you never really get to think or study. If you study this in a laboratory, you study carbon, you can see that these elements are so stable. Being able to feel that is kind of weird, kind of cool, kind of feeling, of older than the earth. It's kind of an interesting thing to think about. If you think about it. You're going to draw that right there. This is on the board. See on the board? It's an abundant element in your body. What's the percent? Write it down. What's the second most abundant element in your body? Carbon. What's the percent?
18%.
Write that down.
These valence electrons are involved in the